Thank you, Dr. JC. Can you guys hear me and see my slides?
Yes, very well.
Okay, good. Welcome to the CIA, and thank you for the CIE invitation today. I'm honored to speak about this sustainable power with energy harvesting here today. As you all know, the power outage hit Texas, and think about it, if we have energy harvesting, we don't need the power grid as much, and it definitely helped us to survive the winter storm while some of these can still be running, of course, while the grid being fixed. So some background about myself. My study is focused on electronics, but throughout this slide, actually, I want to show is the energy harvesting beyond the electronic requirement. It also requires a lot of innovations in terms of material science, chemical engineering, and mechanical engineering. I hope this talk gives you some brief overview of where the innovation need to be and give you some overview of how these energy harvesting is used in a daily life and affect us. So first of all, couple applications I want to show for energy harvesting. Some of it out of the convenience. For energy harvesting, we can have it at home. For example, in the remote control, you put an energy harvesting device in, and you never have to change the battery again. We are all lazy, and we don't want to look for a battery. Or we're being environmental friendly and environmental sustainable. We don't want to throw away those AA battery all the time. In other cases where you're biking and you want a health monitor wearable to monitor your heart rate, oxygen concentration stuff, you really want to use the vibration energy to help to monitor that. That will help to power up those wearable devices. In some other cases, more necessity, where a battery or a cable is not feasible. For example, in the heart implant, where changing a battery is really not practical, right? That's a life and death situations. In other hands, there are some harsh environments in the oil rigs and pipeline where you want to monitor the health of the pipelines. Is there a breakthrough, there's a leak, or there's an earthquake? You want to report it and send out the maintenance crew without having a big installation cost of all these electronics. Energy harvesting comes very handy to reduce some of these costs and help to maintain this system in high functional state. Finally, some of the very popular application you sure heard about Industry 4.0 initiative, where we're putting a lot of sensor out there in the factory to monitor vibrations or any abnormality of the machines, where we can do preventive maintenance. All of these electronic or sensors require electricity or energy. So energy harvesting come into a big position here, having not have to rewire the whole factory. On the other hand, on the consumer space, I'm sure you heard about unmanned retail store, where you can go in and have talk to nobody, interact with no human, and just take the goods and pay with your apps. All these systems require electronic to be powered, sensor to be powered, video camera to be powered, where it can sense where you are and do the accounting and the payment process. However, one of the big challenge is in the unmanned store is the wiring. Wiring is a big cost. The copper cost to wire the whole store in order to power all the electronics is actually the biggest challenge or bottleneck to make this happen. Energy harvesting come into place in all these places to make this happen. In general, I say energy harvesting is where most popular is when connectivity, all-day connectivity is required. It's data-driven. You have to do a lot of sensing and drive a lot of data output, and also require low power applications where you don't really want to burn a lot of power, keep everything in a very low energy mode. Taking a look at another deeper example of how does energy harvesting or IoT help in a factory or office environment. These days, we want to save energy, save our carbon footprint. So one of the popular ways to do it is with the energy harvesting, you can put a lot of sensor nodes in the office or even in the factory, right? You can put light sensor, ambient light sensor, carbon dioxide sensors, motion sensor, and these sensors all require energy to run on it. Today, we're going to introduce a couple of the energy source, basically that's all year round and sustainable that can power up these electronics. And these electronics can talk to each other so that they can optimize the whole office or factory space in order to have a maximum energy usage. So to sum it up, there's a couple things that we're looking for when it makes sense to deploy energy harvesting. First of all, we don't want, when it's really difficult to hardwire power to these electronics, the cost become very high. Like the unmanned store example I talked about, you literally have to wire thousands and thousands of cables in order to power it without energy harvesting. But if we can take the store light and start generating powers, then all these wiring costs are out and make it easier to deploy these technologies. The second one is most of all probably charge our smartphone every day. Imagine if we put battery in the store in these devices, IoT devices, and you have to charge it every day. It's almost inconceivable that every employee, the first thing they go to a store is to go charge the battery. So where energy harvesting makes sense is when battery replacement is not practical or even economically feasible. Finally, you want a battery life. If the battery is very long lasting, meaning we harvest it, the more energy we harvest, the less battery need the less the battery need. So the less often we need to change these batteries. So energy harvesting becoming a more viable and economically makes sense. Next, let me show an overview of what an energy harvesting system looks like. On the left-hand side is the energy input. There's a variety of that, and I'm going to give a little bit more detail about some of these. You got the really low power RF energy, which just coming through the radio. However, you can see the energy level is very low, up to the high power where the solar panel, we even have solar farm, right? Those are all part of energy harvesting source. Then we have the application where we drain the battery, we drain the energy. These require low power applications. Typical components of these is we need the sensor to collect the environmental information, whether this is vibrations or light intensities or humidities, stuff like that. We take all this information, we process it, and we use a radio. Why? We use a radio to send out all this information to the central location, to the cloud, so that it can process it and really coordinate the whole environment accordingly based on all these input. Now, in order to enable all this happen, all these electronics need an energy storage source. So popular source are batteries, and we're going to talk about some other energy sources that are popular. To put all these together, we also need the electronics. The electronics is all put these together from the input to the output. Now, I really want to emphasize there's really multi-disciplined approach to this energy harvesting system. In the middle of it, you got chemical, mechanical experts working to make all these solar energy collections, thermal connections, harvesting happens. You got chemistry experts trying to make the battery more capacity, higher density. You got the electronic expert trying to make sure the most energy conversion from the input to the output. So this is really harvesting is really a multidisciplinary engineering approach to the problem. So first of all, talking about energy source, there's really, we really have abundance of energy around us, whether that is light from the solar, vibration, there's vibration that coming through like on the bridge, on the construction, on the service, or even from human motions that's coming through the vibrations. There is thermal, human body have emit thermal energies. Also, we can take the geothermal energies to power even higher power systems. But in general, for harvesting, we're talking about lower power. Also, even think about the radio wave. We can collect the radio wave and provide wireless power into the system. Now, all these energy have its own limitations. Not everything is suited for harvesting purpose. It really depends on what's your applications. For example, in the RF area, really you can see this is from a low to a high power, harvested power. The RF presented the lowest one is about the highest, even a 0.1 microwatt to the light using 100 microwatt. That's about 1,000 times more energy. If you look at from the application side, the most common, or I guess the very first energy harvesting applications actually is a watch, where we years and years ago we already starting to harvest vibration energy from the watch to keep it running, the kinetic energies. Those are in the low spectrum of the energy requirement, where you only need about 1 microwatt, right? Up to on the right-hand side, a headphone, where you need 60 microwatt. Think about a headphone. If I have to power 60 microwatt power while I'm indoor using a light, which can only provide 100 microwatt, I need to provide a surface area about 600 centimeter squares. That is a pretty big area. That means you have to cover up the whole headphone in order to generate enough energy to run the headphone. So that is a major challenge, how to harvest as much as energy we can and use it efficiently to power such a things. Now, of course, if we talk about smartphone, that is 15 times even higher, roughly 15 times higher than this headphone. So that requires even more areas. And the other problem is the smartphone is running in a different environment. Sometimes you're indoor, sometimes outdoor. So different characteristic or different material is needed to convert those light energy into usable energy. Feel free to stop me if you have any questions. Let's take a deeper look at how to harvest light energy. A very basic concept to harvest light energy is use a so-called a PN junction. It's a semiconductor material through the photovoltaic effect. Basically, it's in general, in the common term, is taking the light and generate electron-hole pairs, which converted to energy. The energy itself is proportional to the intensity of light, the wavelength of the light. So there's a difference between how much energy or what type of material we need, more sensitive to outdoor light versus the indoor light, because of the different wavelength of the light. On the bottom here, I show two very kind of common solar energy harvesting material. On the left-hand side, this is more rigid, more of a home use solar panel type material. The right-hand side is more of a indoor use. This is a flexible panel that you can use in a lot of portable electronics. You can even kind of stick it or glue it together to the electronics to make it fit the form factors of the electronics. From the photoelectric cell itself, there are two different connectivity configurations available. The first is the series, so-called, you can stack up these solar panel or solar boards in series. In this example, I'm showing 4. This is called series configuration, where the solar panel could output a higher voltage. Imagine each of them can output 2 volts. So you can have 8 volt of solar voltage output. So with the high voltage, actually the benefit is easier to convert the energy to usable form. However, think about if you have one of these board broken, one of these panel broken, or dirty, or the sunshade is different, the light shade is different, it's going to limit the whole output of these strings. So there's definitely an advantage and a disadvantage of using the series solar cell. On the other hand, you can put this solar cell in parallel, which in this case, you'll have 4 of these together, and total, it will output 2 volts. Now the voltage is lower, so we must boost up the voltage from 2 volt to maybe 4 or 5 in order to make it usable for other electronics or compatible to other electronics. Now the shading is or status or these configuration of the shading is less effect for these cells, because if even one cell is more shady, receives less energy, it only output less energy, but it doesn't affect the whole total system as much as the series solar cell. Overall, for series solar cell on the left-hand side, it's more suitable for the grid structure where you have a collected solar energy, kind of like a solar roof to power the home system for high power system. For the right-hand side, it's more suitable for energy harvesting, because in general, our harvesting source doesn't require our energy load is low, and the power is usually low power, and we don't really have to put a lot of these in parallel to power the system. And it also makes the maintenance a lot lower. As you can see, if one of them is broken, it just reduces the energy source, right? It doesn't completely take the equipment out of use. So for the vibration side, it uses a different mechanical system. It uses so-called a piezoelectric element to harvest the mechanical energy. When this thing vibrates, when the input vibration, it converts that vibration into electrical charges. In this kind of piezo system, the mechanical mass and stiffness of that dictate how much energy it can generate. Also, the mechanical vibration have some mechanical loss, so we want to minimize that in order to maximize our output. However, I want to stress that in general, the vibration energy harvesting can collect a lot less than the solar, and it's a lot much harder to put this in parallel in order to generate a lot more energy compared with the solar. So you can refer to the other pages I have that this is at least 10 to 100 times different, a lot smaller than the solar energy can generate. So it also limits its application where the loading or the output need to be use a lot less energy in order to make this sustainable. Now this is all about the energy source. Now turning our focus to the energy storage, let's think about what are the requirements to have a good energy storage system. Of course, it needs to have the capacity size to store the available energy, right? If we don't have enough capacity to run or to store this energy, the energy would be wasted. However, when thinking about the capacity, there's also a couple important factors. For example, the energy per weight, the weight density, like the heavier it is, probably more undesirable to carry around in a wearable, but it might be okay if you install a fixed location. Volumetric energy density, meaning how big a volume it occupies, how much space it occupies. We obviously want it as small as possible, as invisible, as less intrusion as possible. You don't want to put a big lead-acid car battery in the middle of a factory floor. That's not very safe, right? So capacity play an important role for the selection of energy storage. Low self-leakage. What that means is, if I just put that energy storage system out there by itself, how much the energy will leak away? Obviously, we want as low as possible, which is nothing, right? We want all the energy be stored and be directed to more useful applications to the load. We don't want to be wasted. Finally, if you're putting this energy storage in a pipeline, in the oil rig, self-protection is very important. You don't want to put a battery there that have explosion characteristics when damaged, right? That is catastrophic. So two of the popular energy storage environment storage options, they are lithium-ion battery on the left-hand side. These are very common storage elements we use every day in our smartphone or notebook. Some of the characteristics we are very familiar with. It requires daily charging, right? And as you know, the battery, as you charge it more, it loses capacity over 2 years. So that's what we call recharge cycle life. How many times we can recharge this battery? Common number is about 500 to 800 times before you have to throw it away. So if you charge it daily, it probably lasts about 2 years. Physical size is pretty big, depending on capacity. However, they do tend to scale that you can get a lot of capacity out of it. In our phone cases, you usually can have 4 amp hour, 4,000 milliamp hour. In a speaker, in a headphone case, you probably have a 300 milliamp hour kind of a speaker or headphone. Environmental impact-wise, which I want to explain a little bit more, it actually takes a lot of carbon footprint or rare earth material to produce these precious material to produce this battery. And during its production, it does generate pollution. So its environmental impact is relatively high. However, because of the high energy density, we tend to use for high energy applications. There's a lesser heard about storage element called supercap, short for supercapacitors. These are capacitor-like material putting two metal fumes together with a carbon medium to store the energy. In general, it can charge millions and millions of times. Basically, you can guarantee during the lifetime of 10 years of the equipment, you'll never have to worry about it being degraded. They will keep just running. However, it does tend to have lower power density compared to lithium ion, so you heard less of it in some of these daily life high energy applications. However, given its millions of charging cycle and long life cycles, it's actually a very good fit for energy harvesting, where our energy consumption usually is in the 100 microamp domain, and you don't have to, and you want 10-year life cycle. So these supercapacitors tend to be a very good choice for energy storage in the sustainable energy environment. For example, in the factory floor for IoT applications, this is very popular compared with the lithium ion, where it tends to be explosive, and we don't want that. So now we have the energy storage and energy input. We need to think of a way to put it all together, so to speak, to get the input to the output to store it. How do we do that? I just want to take your focus a little bit and talk about how we store water. If you think about how we store water, we pump it from a water source, like a river stream or a drain, through some kind of mechanical electronic system to pump it to a water tower. So what is needed? What makes a good water storage system? We need to pump from a low altitude to a high altitude, right? And we need very high efficiency. That means this pump better not take a lot of work, a lot of energy, so that it makes it worth it to pump it, right? And also, we don't want to waste the water. When we want to pump it, we don't want to have water leak. Or when the system is not running, if the water tower is not running, it's just storing the water, we don't want the water tower to leak. These are all the characteristics of water system. Similarly, actually, for energy harvesting system is very similar. We have the solar panel, or the input energy. Usually it's 1 volt or very low voltage, 2 volt. We want to boost the voltage from 1 volt to 4 volt to store in the battery. We want to have a very high efficient conversion system where we can convert as much of the energy from the input source to the storage element. And in the process of it, we want to run the electronic, and we don't want the electronic to take away a lot of these energies. We want a high efficiency systems. Finally, when this system is not working, or at night for a solar system, you're not trying to harvest the energy, you really don't want the system to leak, meaning to waste a lot of energy to maintain it. So when the system is idle, we want to burn as little power as possible. So here we spend, from my side, my professions, we spend a lot of time to think about these 3 factors. How to pump the voltage up from low voltage to high voltage very efficiently with high efficiency. How to pump it with very little energy so this system is sustainable. If you think about a solar panel or thermoelectric, you only have 100 microwatts or a couple hundred microwatts. If I'm already using, if my electronics using the same amount of energy to convert it, that means nothing is going to the battery. That's not good. So we want to use as little as possible of such energy. Finally, when we also think about, for these kind of electronic, when it's not being run at night, we don't want this to burn much energy. So this is kind of my ideal world for ideal energy harvesting systems. So putting it all together, I just want to flash this once again. For an energy harvesting system, we need a good energy source. And I think my favorite right now is solar. I think the other one is still a little bit ahead of its time, need more innovations and collaboration between different engineering fields. We're relatively okay on the energy storage. Of course, we want higher density is better. A lot of chemical engineering resources, mind intellects are going to this area, how to make the battery more efficient, safer, and higher densities, right? Different materials we talked about. Also on the right-hand side, how to consume it. We want to make the electrical engineer are making these low power applications where the radios burn less power, the sensor burn less power, we take less of the input so that we don't have to collect as much energy. These all make up a good energy harvesting systems. Finally, with all these, I hope I get you excited about the future of energy harvesting and what it can be done and what its limitations. But I want to show this. If you're at home and you have a young scientist at home you want to have some fun with, we actually provide some of these learning kits at TI. It's called Energy Harvesting Toolkit. What it really does, you can experiment it at home. It can collect the solar energy, and it comes with an ambient light sensor, humidity sensor, and even some processing power. You can put programs on it. You can play with your kit, try to sense the light. I have actually friends of mine bought this kit who they play with sensing the light, sensing the humidity, playing out different light patterns to signal different environments as a first step. It becomes pretty fun to control different things as a first step to inspire our young engineers or young future engineers into electronics. So with that, I thank you your time, and I'll stop for a moment if you have any questions.